Good morning everyone. So in this class I am going to solve another problem of parabolic equation by using Laplace transformation technique. Okay, in this the problem is find the solution of the non-homogeneous equation derivative of u with respect to t equals second order derivative of u with respect to x minus h into u. Here x lies between 0 to 1 and t greater than 0 when subjected to the non-homogeneous boundary conditions u of 0 comma t equals 0 and u of 1 comma t is equals to 1 with an initial condition u of x comma 0 is equals to 0. Okay, now let's start to find the solution. So for that one we consider the given equation as derivative of u with respect to t equals second order derivative of u with respect to x minus h into u. Here h acts as a constant. Now apply the Laplace transformation to this equation. So we get Laplace transform of derivative of u with respect to t. This will becomes s into capital U of x comma s minus u of x comma 0, so which is equals to then Laplace transform of second order derivative of u with respect to x. This will becomes capital second order derivative of capital U with respect to x minus, and hence this will becomes h into capital U. Okay, now from the initial condition this value will become 0, so then the remaining is second order derivative of capital U with respect to x minus h into capital U minus, so take it into right side, so minus s into u equals to 0. Here u is common, so we take u as a outside, then the remaining is minus of h plus s. Then this equation will becomes, now look here, so that equation can be represented as second order derivative of capital U with respect to x minus s plus h. So here u is common, we take this as outside, then the remaining is s plus h, so then this equals to 0. Okay, now we solving this equation, then we get the solution is u of x comma s is equals to c1 cos hyperbolic square root of s plus h into x plus c2 into sin hyperbolic square root of s plus h into x. Okay, so this is the solution for the equation, for this equation. Okay, now we already well known about the boundary condition, so from the hypothesis they given the boundary condition. Now we apply the Laplace transform to those boundary condition, so then we get capital U of 0 comma s is equals to 0 and capital U of 1 comma s is equals to 1 divided by s. Okay, now apply these two boundary condition to this solution, then we get c1 is equals to 0 and c2 is equals to 1 over s into sin hyperbolic square root of h plus s. Now substitute these c1 and c2 to the above solution, then the solution will becomes capital U of x comma s is equals to sin hyperbolic square root of h plus s into x over s into sin hyperbolic of square root of h plus s. Okay, now we apply the inverse Laplace transform on both sides of this equation or this solution. So now look here, we apply the L inverse, so L inverse of u of x comma s is equals to L inverse of this function. So then here we find the L inverse, so we get u of x comma t is equals to, from the RHS, so we find the L inverse, so this we find by using Maline integral form. So we get sum of residues of e exponential of s into t into u of x comma s at its possible poles. Now look here the poles of u of x comma s are s is equals to 0 is a simple pole and sin hyperbolic square root of h plus s is equals to 0. It gives a infinite poles at s is equals to minus n square pi square minus h. So here n varies from 1 2 3 so on up to infinity. Okay, now here we find the residue of exponential power s into t into u of x comma s at s is equals to 0 for simple pole. So in the next we find a s is a infinite pole. Okay, first we find the residue at a simple pole. So now look here, residue at s is s tends to or s equals to 0 exponential s into t into capital U of x comma s, which is equals to limit as s tends to 0 s into exponential of s into t. So here the function is sine hyperbolic square root of h plus s into x over s into sine hyperbolic square root of h plus s. Okay, here not here, this is wrong. Okay, ಇಲ್ಲಿ x ಇಲ್ಲ, ನಿಮ್ಮ ನೋಟ್ಸಲ್ಲಿದ್ದರೆ ಅದನ್ನ ಸೊ ಎರೇಸ್ ಮಾಡಿಬಿಡಿ. ಓಕೆ, ನಾವು ಲುಕ್ ಹಿಯರ್. So here this one and this one gets cancelled. Now apply s tends to 0. So exponential value will becomes 1. Then so sine value here s is equals to 0. Then the sine will become sine hyperbolic square root of h into x. Then the denominator will become sine hyperbolic square root of h. So this is the residue at s is equals to 0 for a simple pole. So next we find the residue at infinite poles. Now look here, residue at s is equals to minus n square pi square minus h into e power s into t. U of x comma s is equals to limit as s tends to minus n square h square minus h, sorry, n square pi square minus h into exponential of s into t into sine hyperbolic square root of h plus s into x over sine hyperbolic square root of h plus s plus h into square root of h plus s into cos square root of h plus s into x over 1 over 2 into 1 over 2 into square root of h plus s. ಇಲ್ಲಿ ನಾವು ಸೊ g of x divided by h dash of x ಅನ್ನೋ ಒಂದು ಫಾರ್ಮುಲಾನ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಯಾವ ರೀತಿ ಅಂತ ನೀವು ಸಾಲ್ವ್ ಮಾಡಿ ರೆಸಿಡ್ಯೂ ಫೈಂಡ್ ಔಟ್ ಮಾಡೋದು ನಿಮಗೆ ಗೊತ್ತಿದೆ ಅಲ್ವಾ. ಇಲ್ಲಿ ನಾನು ಮತ್ತೆ ಸೊ ಯಾವ ರೀತಿ ಅಂತ ಹೇಳೋದಕ್ಕೆ ಹೋಗಲ್ಲ, ನೀವು ಮನೇಲಿ ಕೂತ್ಕೊಂಡು ರೆಸಿಡ್ಯೂನ ಫೈಂಡ್ ಔಟ್ ಮಾಡಿ ಯಾವ ರೀತಿ ಅಂತ ಅರ್ಥ ಆಗುತ್ತೆ. ಓಕೆ, ನಾವು ದ ರೆಸಿಡ್ಯೂ ಆಫ್ ದಿಸ್ ಫಂಕ್ಷನ್ ಬಿಕಮ್ಸ್ 2n pi into minus 1 over n all to the power n into exponential of minus n square pi square plus h into t into sine n pi x over n square pi square plus h. Okay, now we substitute these two residue in the solution. Then we get the required solution as u of x comma t equals, so residue of it is a residue of simple pole and this is the residue of infinite poles. Okay, now sine hyperbolic square root of h into x divided by sine into square root of h plus 2 pi into, okay, so summation n equals to 0 to infinity n over n square pi square plus h into minus 1 all to the power n into exponential of minus of n square pi square plus h into t into sine n pi x. Okay, so this is the required solution for the given problem. Okay, so in the next class, so I'll solve another problem, means last problem for the Laplace transformation method. Okay, thank you.